Hello friends, welcome you all to our YouTube channel Basics of Physics. In our Modern Atomic Physics lecture series, today we'll be having a lecture based on the fine structure of hydrogen atom. In our earlier session, we had seen what is spin orbit interaction energy, why this spin orbit interaction term occurs in the energy level of an hydrogen atom. Today we'll be calculating this spin orbit interaction energy with reference to the hydrogen atom, and depending upon that one we'll be preparing a new energy level diagram for an hydrogen atom, which is known as a fine structure of hydrogen atom. So let us start with our today's session by just recapping the our previous lectures, some key points, and considering those key points we will go ahead with the today's session. So we had seen yesterday what is spin orbit interaction, but for the sake of information, let me tell you the interaction between the electron spin magnetic moment, which electron has intrinsically, and the magnetic field which is produced by a nucleus motion around the electron when we are looking at the nucleus from the electron's frame of reference. This interaction between the spin magnetic dipole moment and the magnetic field of the nucleus, this interaction that is called as the spin orbit coupling or spin orbit interaction that we had seen yesterday. In order to visualize it, you can consider that in an hydrogen atom we have a proton or nucleus situated at the center, and electrons are revolving around the nucleus. This picture we had seen in our earlier classes as well. If you consider the same picture from the electron frame of reference point of view, in which electron will be situated at the center and nucleus it will move around the electron. Okay, that is a electron frame of reference. Now in this one we know that electron has an intrinsic spin. Okay, so associated with that it will have a spin magnetic dipole moment, and when we are looking from an electron frame of reference, this nucleus moves around the electron. So yeah, we know that any moving charge particle constitutes a current, and that constitute current it will give you the some magnetic field. So that magnetic field, this electron which is situated at the center, it will experience. So the intrinsic spin magnetic moment which we have considered, or which is given by the mu s, okay, which is given by mu s, and the magnetic field, let us say it is B, which is experienced by this electron due to the orbital motion of this electron, orbital motion of this nucleus. That interaction that we call it as an spin orbit interaction. Now we know that whenever the magnetic dipole and magnetic field they will interact, they will have a certain orientation potential energy. So this magnetic orientation potential energy for a spin orbit interaction, it is given by minus mu s dot b bar, that we had seen our earlier lecture. Now if you consider this electron spin interaction energy due to the magnetic field which nucleus, due to the orbital motion of the nucleus it is created, and the spin magnetic dipole moment of an electron, if you consider this magnetic interaction energy, it will have a two orientation. So due to that one, the doubling of spectral lines can be observed, and this doubling of spectral lines can be explained on the basis of magnetic interaction between the spin and orbital angular momentum of atomic electrons. Now you can see over here, we know that the electron can have a two different spin orientation, that is spin up and the spin down. Suppose the magnetic field which is created by this motion of this nucleus, if it is pointed in upward direction, and the magnetic dipole moment associated with the spin part, it is pointed it in a downward direction. If these two are in opposite direction, that will be the one configuration, or if both of them will be in a same direction, then this will be another another way of observing this thing. Now these are the two different orientations which you can have. Due to that one, you'll be having a doubling of a spectral lines in an hydrogen atom. This doubling of a spectral lines in an hydrogen atom, that is called as a fine structure of a hydrogen atom. Now also in the our earlier lecture we had seen this spin orbit interaction energy, which is delta ES. If you consider, that is nothing but the minus mu s bar dot b bar, and we have from Ampere's law and Coulomb's law, and by basic electromagnetic theory we have expressed this b bar in terms of L bar. Yesterday we had seen this, and if we substitute this value in this equation, we can calculate this delta ES is equal to 1 upon 2m square c square 1 upon r dv by dr into s bar dot L bar. Now if you consider this delta ES bar, that is a spin orbit interaction energy, okay, which we have calculated from uh, setting a calculations from the electrons frame of reference. We have calculated that in our yesterday's lecture, and this we have found out that this terms come out to be 1 upon 2 m square c square 1 upon r into 1 upon r into dv by dr into s bar dot L bar. So this spin orbit interaction terms, it depends upon the dot product of the spin angular momentum and the orbital angular momentum of an orbiting electron. Now how this S bar and L bar, they couple each other, and how can we find out this S bar dot L bar to find out this delta S? That is the motto of the today's lecture, and from this one we'll be going ahead with the fine structure of an hydrogen atom. We'll be showing you the energy level diagram for few selected atomic levels. Okay, so here in this figure you can see that spin angular momentum, orbital angular momentum, these are the vectors which we had seen in our earlier lecture, that in a Larmor's precision, that these vectors, they align in a particular direction, they precess around a cone in this fashion, which is you can see within this animation. And this L and S, they will vectorially you can add to give the total angular momentum, that is nothing but the capital J. Now we have to see this, we have to consider this L bar, S bar and J bar to find out the value of S bar dot L bar. So let us start to find out this S bar dot L bar, and to express this S bar dot L bar into small l, s and j, we'll consider, we know that this J bar, that is nothing but the total angular momentum, which is a vector sum of orbital angular momentum as well as the spin angular momentum. If I take a scalar product of J bar with J bar itself, then I can write J bar dot J bar is equal to L bar plus S bar dot L bar plus S bar. So if I substitute and if I simplify this, I'll just do a simple horizontal method of multiplication. First factor into second bracket, which is L bar dot L bar plus S bar. Then second factor with sign, which is plus S bar, into second factor as it is there, which is L bar plus S bar. Now remember, it's a dot product of two vector. If I do this multiplication, that is L bar dot L bar plus as it is L bar dot S bar. For second bracket it is S bar dot L bar, and for last term it is S bar dot S bar. Now we know that L bar and S bar, these are the vectors, and we are talking about the scalar product of these two vectors. And we know that scalar product is commutative, means A bar dot B bar you can write down is equal to B bar dot L bar. So similarly on the same ground you can write down L bar dot S bar is equal to S bar dot L bar. And similarly for a vectors cross dot product of two vectors, it will be nothing but it will be the square of that vector. So J bar dot J bar is equal to J square, L bar dot L bar is equal to L square, and similarly S bar dot S bar is equal to S square. So if I use these values in these equations, what I'll get J square is equal to, for J bar dot J bar I am writing J square, L bar dot L bar I am writing L square. For L bar dot S bar I am writing S bar dot L bar, because this vector scalar product is commutative. So this will be, and third term it will be as it is, and for S bar dot S bar I am writing S square as it is. Now, if I further simplify this, L S bar dot L bar S bar dot L bar, I can write it as an 2 S bar dot L bar. And if I use this one, If I transfer this L square and S square from this side to this side, it will be J square minus L square minus S square, which is equal to 2 S bar dot L bar. Now, if I transfer this 2 from this side to this side, it will get divided to this term. So from this expression, we can say that S bar dot L bar is nothing but J square minus L square minus S square divided by 2. That is a value of dot product of a spin angular momentum vector with the orbital angular momentum vector. Now we know this spin angular momentum vector or orbital angular momentum vector, they can have a quantum mechanical values, and we had seen this in our lower classes. This J can be written as J into J plus 1 H cross, square root of J into J plus 1 H cross. L can be written as L into L plus 1 H cross, and S bar is equal to S into S plus 1 H cross. These are the basic relations which we had seen our undergraduate courses, and even you can go through the vector atom model, there you will find out this one, or you might be studying this in terms of the this in the quantum mechanics course. So if I substitute these values in this equation, so square of J, it will be square root we will remove, and this H will be H cross square. So each term will have a H cross square. So I'll take H cross square common, and this 2 I will be writing outside. So it will be H cross square 2 outside. For the J square, it will be J into J plus 1. For L square, it will be L into L plus 1. And for S square, it will be S into S plus 1. Okay. So this will be the expression for S bar dot L bar. Now, what we will do next, we will substitute this value of S bar dot L bar in the energy spin orbit interaction energy, because remember we need to calculate the spin orbit interaction energy. If I substitute it in this one, I'll get 2m square c square 1 upon r dv by dr into S bar dot L bar. If I substitute this value of S bar dot L bar from this equation, what I'll get? I'll get the expression in this form: 1 upon 2m square c square 1 upon r dv by dr into h cross square by 2 as it is, and this quantity in the bracket. Now, for any state, this spin orbit interaction energy is nothing but the expectation value of the this energy delta es, that is delta es expectation value. And this delta es expectation value we will be calculating for an hydrogen atom. So we have to consider the potential for an hydrogen atom, and you have to, by using the wave functions for an hydrogen atom, we have to calculate this expectation value of 1 upon r into dv by dr. So to find out the expectation value of 1 upon r dv into dv by dr, or this which can be written as in this fashion as well, which you will study in the quantum mechanics for a hydrogen atom. This can be calculated for an hydrogen atom by considering the potential. For a hydrogen atom, the potential is Ze square upon 1 of 4 pi epsilon 0 r. If I take the derivative of this one, Ze square upon 4 pi epsilon 0, it will be constant, and derivative of 1 upon r will be minus 1 upon r square. This minus and derivative minus, it will become plus. So dv by dr is nothing but the Ze square upon 4 pi epsilon 0 1 upon r square. Now in order to calculate 1 upon r into dv by dr, it will be nothing but you just have to simply multiply this term by this 1 upon r, which will be 1 upon r cube into Ze square upon 4 pi epsilon 0. Now remember, we have to calculate its expectation value. Now in order to calculate the expectation value, we'll be using a simple quantum mechanics assumptions. So that is nothing but the psi star into quantity whose expectation we need to calculate into psi. Its integral over a whole space. So it's a volume integral because it's a three-dimensional problem. Now we know that for a hydrogen atom, if you consider this psi can be written as in terms of R and L. We had seen in our earlier lecture what are the wave functions for an hydrogen atom in terms of R and L and theta and phi. So theta and phi part for an hydrogen atom, it will give you the straightforwardly 4 pi r square, and it will give me R and L star into R and L into 1 upon R dv by dr into dr. Now if I substitute this value of 1 upon r dv by dr in this equation, which is nothing but the z e square upon 4 pi epsilon 0 1 upon r cube. If I substitute this value, I'll get 1 upon r dr dv by dr, its expectation value is equal to this 4 pi. In this case it will cancel with this 4 pi, and this r square it will cancel with this r cube. Okay, so in the bracket you will be getting rnl star into rnl into 1 upon r dr. By using the quantum mechanics rules, you can work out this mathematics. If you work out this mathematics, will not be working, will be calculating this derivation over here. But if you do this calculation, if you make a back substitution in the energy eigenvalue or expectation value of this spin orbit interaction energy, it will be nothing but 1 upon 2 m square c square h cross square by 2 into j plus 1 minus l into l plus 1 minus s into s plus 1 into 1 upon r dv by dr. If I substitute this expectation value in this expression reduces to z raised to 4 alpha square r divided by n cube l into l plus half into l plus 1 into j plus 1 l minus l into l plus 1 minus s into s plus 1. That will be the expression which will be getting for an spin orbit interaction energy. In this expression, what is this alpha? This alpha whose value is nothing but the 1 upon 4 pi epsilon 0 e square upon h cross c. This is called as the fine structure constant, and whose value is 1 upon 137. And what is this r? This r is called as the Redbox constant, whose value is z square m e raised to 4 uh, upon 8 epsilon square h cube into c. That is a Redbox constant. Now we know that uh, the spin orbit interaction, it is occurring due to the interaction between the spin magnetic moment of an electron and the magnetic field, which is arise due to the nucleus motion around the electron. Now we know that the electron can have only two spin configuration, plus half and minus half. So your angular momentum quantum number J, it can go from minus L minus 1 half to L plus 1 half. Though, so the effect of spin orbit interaction is to make the state J is equal to N minus half to have lower energy than with the J is equal to L plus half uh, state. Now for s orbitals or for s state electrons, we'll be calculating this energy. Now what is this energy for s electrons? For s electrons, we know that L is equal to 0, and any electron, it has a s is equal to 1 half state. So if you calculate the value of J, which goes from L minus s to L plus s, so as the value of L is equal to 0, so value of L will be 1 half only. So if I substitute it in the formula of expectation value of the spin orbit interaction, which is delta ES bar is equal to hc by 2 into this bracket into j plus 1 minus l into l plus 1 into minus s into s plus 1. If I substitute it in this expression, what I'll get for j, I have to substitute 1 half, so it will be 1 half as it is. It will be 1 half as it is, 1 half plus 1, 1 half plus 1 minus value of l, it is 0, so it is 0 into 0 plus 1 minus s is 1 half, so it is 1 half into 1 half plus 1. So this first bracket and this third bracket, these are equal and they are opposite in sign, so they will cancel each other, and this 0 into anything, it will be 0. So 0 multiplied by this constant, you will get the answer 0 over here. So thus we can say that for s electron in an hydrogen atom, the expectation value of a spin orbit interaction energy, it is coming out to be 0. So this is very important result for a ground state of an hydrogen atom. The spin orbit interaction energy is always 0. Okay. Now we will consider what will happen to the higher energy levels, that is 2s, 2p, 3s, and so on. Here we will calculate the what is the doublet separation between the two adjacent levels for an hydrogen atom arising due to the spin orbit interaction. So for this purpose, what we will consider, we'll be considering this energy expression, spin orbit interaction energy, which is nothing but the delta ES, which will be SC by 2 into this term. Okay. Now for doublet separation, let us say delta nu is the doublet separation between the two energy levels with J is equal to L plus half and J is equal to L minus half. So in order to get the doublet separation, what we have to consider, we have to just use a simple Einstein's energy formula, that is the energy difference between the two states divided by H. It will give you the doublet separation frequency. So this doublet separation frequency we will be calculating by delta nu is equal to energy for the first state, which is J is equal to L plus half, and minus energy for the second state, for which J is equal to L minus half, divided by the Planck's constant. It will give us the that doublet separation frequency. Now we will try to calculate this value delta ES for J is equal to L plus half over here. So in this energy expression which is given on the top, okay, we will substitute the value of J is equal to L plus half first, and we will subtract that from the J is equal to L minus half. So for the first term, instead of this J, I am substituting it is L plus half. Similarly, it is L plus half over here. And for L, I am not doing anything. We will be keeping as it is. For S, we know that the spin of electron, it is 1 half. So it is 1 half into 1 half plus 1, minus for the second term value of J, it is nothing but the J is equal to L minus half. So instead of J, I am substituting L minus half. Here also L minus half. The L term I am keeping as it is, minus 1 half into 1 half plus 1, that is for the spin, because S has a value 1 half. Now if we simplify this further, L plus 1 half plus 1. So 1 half plus 1, it will give you the 3 by 2. And similarly, we can do for the this 1 half plus 1, that will be 3 by 2. And this, if we multiply this by 1 half, then it will be 3 by 4. Similar is the case for the last term, which will be 3 by 4. And if you simplify this, L plus L minus half plus 1 half, it will come out to be L plus 1 half over here. So this will be the further simplified term. If you further simplify the first term, we will keep it as it is, L into L minus L into L plus 1. This is minus and this is minus. So this term, it will cancel with this term. So L term will cancel. 3 by 4 minus 3 by 4, they will cancel each other. So what you will get, just only, it is L plus half into L plus 3 by 2 minus L minus half in bracket L plus 1 half. So these are the terms which you will getting. Now here you can see in this expression you have a L plus half term in the first term, and in the second term you have the L plus half term on the last. So it is L plus half, you can take it outside. So it is, you can write L plus 3 by 2 minus L minus 1 half. L plus 3 by 2, that is second term we are writing as it is, minus this term will be as it is, which is L minus 1 half. Now from this one, if I open this bracket, it will be this L will cancel with this L. So this will be 3 by 2. This minus becomes plus. So it will be plus 1 half. So 3 by 2 plus 1 half, that will be 4 by 2, which is nothing but 1 half. So these two will cancel with these two. So finally you will get an expression, that is the energy frequency doublet separation, frequency of separation between the two doublets for due to the spin orbit interaction. It is nothing but the CZ raised to 4 alpha square R in divided by n cube L into L plus 1. From this one, what you can say, that the spin orbit interaction doublet separation, it is independent of J. So it does not depend. There's a separation frequency between the two doublets of an hydrogen atom. It does not depend upon the J, but it depends upon only the orbital angular momentum quantum number and some principal quantum number. This doublet separation depends upon the principal quantum number n and orbital quantum number, that is small l. And the modified rule for this one electron atom transitions are nothing but delta L can take any value, means you can have a transition between n equal to 5 to n equal to 1 or n equal to 3 to n equal to 1. You can have any transition. There is no restriction on the principal quantum number, but the restriction on the quantum number L, it is delta L is equal to plus or minus 1, and this delta J is nothing but it can take value 0 and plus or minus 1. So these are the modified selection rules for an one electron atom. Now we will prepare an energy level diagram for based on the earlier results. We had seen that in an hydrogen atom we have a different energy levels. For n is equal to 1 you have E1, which is a minus 13.6 electron volt. For second energy level you have a minus 3.4 electron volt. For E3 you have a minus 1.4 electron volt. For n equal to 4 you have a minus 0.8 electron volt, and so on. For each quantum number we know that we can have a different values of L. For example, for n equal, you can have n equal L equal to 0, you can have a L equal to 1, L equal to 2, L equal to 3, and so on. L equal to 0 corresponds to S orbitals, or we call it as an S series. L equal to 1 corresponds to term symbol P, L equal to 2 corresponds to D, and L equal to 3 corresponds to uh, F series or F level. Now you can have from the given selection rules, we can have is that we can have a transition from any level to the L equal to 1 level, or you have a transitions from L is equal to 0 to L equal to 1, because we know that delta L can have a value plus or minus 1. Delta L can have a value plus or minus. So L is equal to 0 to L equal to 1 transitions are allowed, and that series is called as the S series or sharp series it is called as. Similarly, you can have a transitions from L equal to 1 to L equal to 0, and that series is called as the principal series. This series is called as the principal series, because L equal to 1 to L equal to 0, that is also allowed transition. Similarly, if you have a transition from L equal to 2 to L equal to 1, that is called as the diffuse series. That is called as the diffuse series because the transitions are coming from the D level for which L is equal to 2. So that is why it is called as the diffuse series. And if the transitions are from the L is equal to 3 level on the different levels, then it is called as the fundamental series. That is called as the fundamental series. So this energy level diagram is similar to the way in which we have considered for an hydrogen atom energy level diagram based on the Bohr's theory. Now, depending by considering this energy level diagram, now we will be calculating what is fine structure energy level diagram for an hydrogen atom. Now consider the splitting due to the spin orbit interaction of some of the hydrogen atom energy levels. We know that you have a different orbital. Let us say 1s level is there, then 2s level is there, 3s level, 4s level is there. You can have this angular momentum value for this s orbitals or s levels, because we know that for s level L is equal to 0 and L is equal to 0, so and s is equal to 1 up. So if you calculate the total angular momentum quantum number, which is given by L plus s or L minus s, then this L plus s or L minus s, it will be nothing but 0 plus 1 half minus or 0 minus 1 half, which will be nothing but the 1 half over here. So for these S levels, there will be only one single level will be there. That is nothing but that will corresponds to J is equal to 1 half. This is a normal energy level diagram. Now due to the spin orbit interaction, what exactly happens, that we will be looking. Now for 2p level, if you consider for 2p level, what you have for 2p, L is equal to 1. For p level, you have a L is equal to 1 and S is equal to 1 half. So depending upon that one, L plus S, that is 1 plus 1 half, it will give you the 3 by 2. L 1 plus 1 half, that will give you the 3 by 2, and 1 minus 1 half, it will give you the 1 by 2. So for a given P level, you can have two total angular momentum quantum number J, corresponding to J is equal to 1 half and J is equal to 3 by 2. Similarly, for 3P level, you can have J is equal to 1 half, J is equal to 3 by 2. Similarly, for 4P level, you have J is equal to 1 half and J is equal to 3 by 2. So for each P level, you have a two J levels corresponding to J is equal to 1 half and J is equal to 3 by 2. Similarly, what will happen to the D level? For D level, we know that for D level, L is equal to 2 and S is equal to 1 half. So 2 plus 1 half, it will be 5 by 2, and 2 minus 1 half, it will be 3 by 2. So you can have 3 by 2 and 5 by 2. You have J value, it will be 3 by 2 and 5 by 2. Similarly, for the 4D electrons, L is equal to 2 and S is equal to 1 half. So 2 plus 1 half, that will be 5 by 2, and 2 minus 1 half, it will be 3 by 2. So for D levels also, you will have two sub levels. So now you can consider over here a single 2s level, it will be as it is, but P level, it will be splitted into the two different energy levels, that is 2p 3 by 2, 2p 1 half, 2p or 3p 1 half, 3p 3 by 2, or 4p 1 half, 4p 3 by 2. Similarly, the D energy levels, it will be splitted into 3d 3 by 2 and 3d 5 by 2. Similarly, 4d 3 by 2 and 4d 5 by 2. Now, what are the different transitions it will be possible in this case? By considering the selection rules that delta L can take value plus or minus 1 and delta J can take a value 0 or plus or minus 1. So you can have the transitions between uh, J equal to 1 half to J equal to 1 half, because that will give you the delta J change to be 0. And if you consider this delta L in this case, from S to P transition, delta L is plus 1, so that is also okay. Next transition, it can be from 1s to 2p 3 by 2 level. So it is 1 half to 3 by 2 level it is going. So if you calculate the delta J, it is 3 by 2 minus 1 half. 3 by 2 minus 1 half. If you calculate 3 by 2 minus 1 half, that will come out to be plus 1. So that is also valid transition. Okay. And but if you consider a transition from 1 half to 5 by 2 level, that will not be allowed, because 5 by 2 minus 1 half, it will give you the 2, and which is not allowed as per the selection rules. Okay. You can have the another transition from 1s 1 half level to 3p 1 half level, because for 1s to 2p, delta L is changing by plus 1 and J change is, it will be 0. So this transition is okay. You can have a transition from 1s 1 half level to the 3 by 2 level, which will be also okay, because 1 half minus 3 by 2, it will be minus half, which will be okay with the delta J selection rule, and also delta is equal to plus 1, so that is also okay. This energy levels which we have considered just now, this is called as the fine structure of an hydrogen atom, and for this fine structure of an hydrogen atom, the selection rules, these are given over here. Okay. And in addition to the energy levels which we have calculated by using a Schrodinger's quantum mechanical equation, or the uh, Bohr's model, you can see that these energy levels, it will be doubled in this case. So in this case, initially we were having the transition from 2p level to 1s level, or you were having the transition from 1s level to 3p level. Now in addition to this one, you will be having a one more transition from 1s to uh, 2p level. If you find, you can have these two transitions. Similarly, from 1s to 3p, you have these two transition. That is why the reason we called it in the initial, that doubling of the spectral lines due to the fine structure of an hydrogen atom. So this which we have discussed, this is called as the fine structure of an hydrogen atom. Here you have to remember just the thing, what are the selection rules, and if you are having an competitive exams questions based on this one, you just have to remember these basics rules. And what is the term difference, the separation between the spin orbit interaction energy doublet separation, on which it depends. That is an important result. I'll suggest you people don't worry about the mathematics which we have worked out for a spin orbit interaction energy calculation. That is, no one will be going to ask you in the exam that much rigorous mathematics. But for your understanding purpose, being a physics student, you should be knowing that how these results are derived. So for the sake of simplicity purpose, for your understanding purpose, for your knowledge purpose, I had shown those calculations over here. I hope you people have understood. Uh, that's it for the today's session. We will stop here for today's lecture. I hope you people have enjoyed the today's session. If you have not subscribed to our channel, I request all you people to please subscribe the channel Basics of Physics by Professor Ravikiran Latte, and please like the videos and comment if you have any suggestions based on the today's content. That's it for the today's session. We'll stop here for today's lecture. Thank you.